Well, hello again. Today we're going to have a look at an application in the area of differential calculus, and this is Applications of Differentiation, and it's entitled Linear Approximation. Now, I've used a nice graphy background there because this is all about approximating basically small changes in a function, and it's sort of like a graphy kind of application, really. And to that end, I'm going to explain it to you in great detail on the next screen. Now, I want you to listen very, very carefully because this is a misunderstood area. Really, really badly misunderstood. First of all, I want to show you, as I've got on the screen there, any old function, y is a function of x, but it has to be a curved function. It could curve that way that you see there, such as a right way up parabola, y equals x squared plus 1, or something similar to that, or it might curve the other way, such as a y equals root x function. It doesn't really matter, but the technique applies to when the graph is curved, okay, and it's approximate. It's an approximation technique. It's not accurate mathematics at all, okay. Now we'll take a known point, x0 and y0. We know both x and y at ground 0, okay, which is the point that we know on the graph, okay. You've got that locked in. We know x0 and y0. For example, 1 and 2, or something like that. Now, so there's x0, okay, and I've drawn in, do you see that I've just sneaked in the tangent line at the graph where x is x0, because that's very important, that tangent line. That is the basis of the approximation technique that we're going to use in a moment. Now, so what is it we're trying to approximate? Well, funny you should ask that. Actually, you see that point that I've just drawn in there, that's x1 and y1? Well, x1 is known, but we assume for the sake of linear approximation that we don't know y1. y1 is the thing we have to estimate, okay? It's the one we're trying to work out. Now you might think, well, hang on a second, don't you know what f of x is? Yes, you do. You do know that, but for the sake of this technique, you'll see as we go a bit further on what we're doing when we're estimating y1, okay? But just lock that one in for now. We know x0 and y0 at ground 0. We know x1, but we don't know y1. We've got to guesstimate it with an approximation technique, okay? Now, so there's x1, and what I've done is I've drawn in delta x, sometimes otherwise known as h. And delta x is a very, very, very small increment in x, from x0 to the point we call x1. Microscopically small, okay? It has to be small for the approximation to be any way valid at all, okay? So I've written down there, delta x is very, very small and is known. It is known, okay? Delta x might be 0.01 or something like that, something very small. Now, okay, the plot thickens. The approximation that we use with linear approximation is as follows, okay? What we do is we neglect the curve of f of x over the very small distance delta x, aka h, and we assume that it is a straight line graph based on the gradient at x0 and y0. In other words, if you were to follow your eye along from x0 and y0 along the path of that tangent line, where you see that little pink tangent line intersecting the vertical dotted line coming down from x1, that is the spot. That intersection spot is where we're going to guesstimate that y1 is, where it, of course, it isn't, but that is our approximation technique. So obviously, the more the curvature of the curve, the less accurate this is. So, and that's why we have to do this over a very tiny, weeny little increment, delta x, such that it is kind of like approximately a straight line, and it hasn't curved away very much from a straight line over the increment from x0 to x1. Okay? That's the whole point of this thing. Okay? Now, I've just put an arrow to point to you that gradient line. That is the secret of the whole thing, that gradient line. That is how we get our estimate of y1. Okay? Now, there's delta x and delta y that I have just put in there on the graph for you. Now, you happen to know what both of those are if you know what the function of x is. Because if you know what the function of x is, presumably you can find the gradient function of that function, and therefore, if you know the gradient function, therefore you can plug in the value of x0 into that gradient function and get the actual numerical gradient at point x0, y0, okay? Now, if you've got the numerical gradient and you know what delta x is, then that's the gradient and the run that you know, and you can just plug that into a very simple formula, rise over run equals gradient, and you can get the rise, which is delta y. Now, that's all this linear approximation mumbo-jumbo is about, getting that little delta y there and adding it to y0, which we know, remember, to get an estimate of y1. Okay? So that is, I've just marked it in there in red, that is x1 and y1. Well, x1 is known, but y1 is an estimate, okay? And that's what this whole confusing mess is about, okay? It's very simple, isn't it, really? Okay, so let's just put it into some maths. We're saying that delta y over delta x, which is the rise over the run, is the gradient at point x0, okay? That's the gradient, where x is x0, ground zero, as I call it, okay? Now, therefore, y1 estimate equals the original y0 at ground zero plus that little vertical delta y bit that I just marked in for you as the rise. And that could be written as y0 plus delta y over delta x times delta x, isn't it? It's just another way of writing delta y. But you know that delta y over delta x is the gradient at point x0, ground zero. So what we're leading around to, getting to here, is we're saying that therefore y0 plus the gradient at x equals x0, dy dx at that point, times delta x, which is the same as the line above, is equal to that thing. That's y0 plus alternative terminology, f dashed x0 times delta x. So that's what we're saying y1 estimate is. It's y0 plus the rise, and the rise is the gradient times the run. Okay, did you get that? It's y0 plus the rise, and the rise is the gradient times the run. That is the formula we use. Now, I've written it up there. So we're saying, therefore, y1 is approximately equal to y0, because it's not accurately equal to it at all. You can see how far out it is by looking at the graph. I'll highlight that for you in a moment. So y1 is approximately equal to y0 plus the gradient at x0 times that delta x. And if the delta x is called h, then the formula takes on its familiar persona. Da-da-da-da, and we'll get Mr. Box to come in and do his work. Thank you, Mr. Box. That is the formula. That is the formula, okay? Y at point 1 is equal to the original point at point 0 plus the little x increment, or h as we usually call it, times the gradient at the original point. Now, you can see in this case, because of the way the curve is curving upwards, you can see that y1 estimate is an underestimate of y1 actual. Just have a look over there. I'm just going to point over to there now and show you what that is. See that underestimate? See, look at the little red cross there, x1, y1 estimate in brackets. You can see that point, and then look upwards vertically to the actual value of y1. You see how much we've underestimated it by. Okay? Now, I think that you can probably deduce from a little logical step that if the curve was curving the other way, such as a y equals root x graph, you'd end up, by doing the same procedure, you'd end up with an overestimate of y1. Okay? Phew. Now that was a lot of explaining, but I wanted to go into great detail to show you what it's all about. It's actually very simple. It's very, very simple, but the way it's explained in textbooks, it gets all very abstract and very gobbledygooky, and you know, the abstraction is the thing which really, really, really ruins a lot of students' confidence with this area. So let's do some now. We'll do some applications of this. Okay, we've got, given that f of x equals x to the fourth minus x cubed, we've got to find in terms of p, oh here we go again, pronumerals everywhere, the approximate increase in f of x as x increases from 2 to 2 plus p, where p is very small. Now, did you see that word approximate? That just, it's a dead giveaway. That means da-da-da-da, linear approximation. Let's go. So we're saying here that x0 is 2, aren't we? Look at it, look at it, look at it. X increases from 2 to 2 plus a little bit, where p is the little bit, okay? And we're saying that delta x, or h, is p, and x1 is 2 plus p, in terms of all the terminology that we used in the previous screen. So, okay, so now reread the question again. What are they asking us for? The approximate increase in f of x. So they're asking us for the delta y bit. That's what they're asking us for. So let's just trot out our formula here. y1 is approximately equal to the previous value at ground 0 plus the little bit of increment in x, which is h, times the gradient at ground 0. Okay? Now, that's right. Approximate increase means yes, yes, that's delta y. The approximate increase is the delta y bit. Okay? So therefore, we're saying that, let's put it in that form. Y estimate minus y0, just rearranging that formula, is approximately equal to delta y, doesn't it? Okay, therefore, yeah, that's right. Now, and that's equal to h times f dashed x at x is 0. Now, just don't lose sight of what those terms mean, and you'll be safe. You'll be okay with this, okay? So I think we've whittled it down to the point that all we've got to do is work out here delta y, and that's just h, which is the increment, which looks like it's p, doesn't it, times the gradient at ground 0. And that means the gradient when x is 2. Well, that's pretty easy, isn't it? Yeah, we know that. That's p. And we know that thing. Well, we will know it pretty soon. We're just going to work it out. F dashed x at x equals x0. So let's do the old dy dx trick. That's the gradient function. Do you agree with me? Look at the function up in the top line and do the derivative in your head. That's good, pretty good. Now we're going to sub in x is 2. Hey, hey, no problem. Therefore dy dx when x is 2 is that thing. And that comes to all that. And that comes to all that. And that comes to 20. So that looks like the gradient of that curve, x to the fourth minus x cubed, is actually 20 when x is 2. Now I think it's all over bar the shouting now, folks. Let's go for this. We've got all the information we need, so that's f dash of x at ground 0, in other words when x is 2. So let's just go and do a snail trail and plug that into our formula for the knockout punch. So we're saying that delta y, the change in y, is approximately equal to h times f dashed x at x equals ground 0, and we've worked both of those things out now, haven't we? Yeah, h is p and the gradient is 20, so it looks like it's 20p to me, for you and me. That's our answer, folks. Is Mr. Box there? Oh, hello, Mr. Box. Wow, it's so nice to see you. So that is the answer. That is the approximate, not the exact, it's the approximate increase in f of x according to this linear approximation technique. Okay? Now, I can't tell you whether that's going to be an overestimate or an underestimate unless I actually look at the graph itself, and then I'd sure be able to tell you. Okay? Alright, how do you feel? See, the abstraction gets you a bit, but if you just keep your head and you realise what you're doing, look, it's not that hard at all. Yeah, I've just written that down in words of one syllable for you, or not really one syllable, but just plain English. Yeah, okay, alright, another one. Now this one here is a bit of a killer diller. This is a worded question which students loathe with a passion, and we have to read it, we have to reread it, we have to underline the key words, and then we have to work out a strategy of what to do, and then we have to do it. Now, come on, we'll read it together. The time for a pendulum of length L centimetres to complete one swing is given by the function with the rule f of L. That's the period, they call that in physics. The period is the time necessary to complete one whole cycle of something which repeats on and on and on. That's equal to k, where k is a constant, times root L, where L is the length of the pendulum. And actually that's how they changed when a clock ran fast or slow in the olden days, like a grandfather clock or the old pendulum clocks, which I can still remember having on our mantelpiece when I was a little boy. We used to just have a little screw which would lengthen the pendulum a little bit, and that would make it go slower. It was really marvellous. Anyway, so if an error is made in the measurement of the length of the pendulum so that the measured length is 2.5% greater than the actual length, find the approximate percentage error. Now there's an extra level of complication in the function f of L, which is used to calculate the time of the swing. Now, did you see that word approximate? That's your cue. Linear approximation, da-da-da-da, off we go. Now, it looks hard, doesn't it? But look, I think we'll just take a deep breath and read the question through. Now, we've already read it through. Now, the next thing we're going to do is reread again, highlighting the important bits, okay? All right, there's our function, okay? I think I'm going to call that thing P for period, to try and help myself with all this abstraction going on everywhere, okay? K is a constant. Well, that means K doesn't matter at all. It just goes along for the ride. That's okay. Now, we're saying that the error in the measurement of the pendulum is 2.5% greater than the actual length. Now, I'm going to have to put that into a more user-friendly format than that, but that shouldn't be so hard. And then we've got the actual length. Yeah, 2.5% greater than the actual length. We have to find the approximate percentage error. Well, we'll find the fractional error first, and then we're just going to multiply that by 100. That's how you work out percentages. Okay, now, yeah, the approximate word is your key. That tells you have to use linear approximation. Now we're going to work out a strategy now. Now, I think the strategy with this is just the same old procedure. You don't lose your cool. You basically work out, we're going to work out the gradient of the function, the pendulum, the period function. We're going to find the approximate change in P, which I'm calling P, the period of the swing. I'm not using F of L. I'm going to use P because it helps my thinking a little bit easier, okay? It makes it easier. Delta P, that's what I'm going to find, the approximate change in P, or delta P, as L changes from 1L, or itself, to 1 plus 2.5 hundredths of L. Now, does that sound right to you? Have a look at the question again. I think it's pretty good. Now, I'm just saying let f of L equal P, okay? Now, that seems like a very, very fine start. In fact, we've pretty well scun it by the time we do that, but there's just a few more steps. Number 2, we're going to divide delta P, which we found in step 1, by P, and times it by 100 to get the percentage change. That is in P, or error as they call it, yeah? Okay, I think that's just about it. Now that's all you've got to do, so just keep your head and do that. Let's go with step 1. Now we know that P is K root L, so what we've got to do is get the gradient function for P as a function of L. And I've got it there for you, okay? Now, we're just going to assume that the pendulum is length L without inventing any more symbols and making life miserable for ourselves. I've just cleaned that up a little bit. Okay, so therefore that's dP dL, okay? So therefore, do you remember the formula for delta P? If H is, that's the little increment in L, if that's 2.5% or 2.5 hundredths of L, snail trail, that's, putting that in even simpler English, is 5/200ths, okay, of L. 5/200ths of L. So we've got our H now, okay? So all we've got to do now is get dP/dL when L is whatever it is. We're just going to call it L, which we've already got. So therefore, we're saying H times F dashed L, or dP/dL as I really should be calling it, is 5/200ths of L times dP/dL at that value of L, which we're just calling L. So that's, I just got that on the left hand side of the screen there. Okay, I've just put root L on the bottom line instead of L to the minus a half. So that's looking all right. Now do you realise what that is? That is delta P. That's what delta P is. That's the change in P. Okay? Now, all we've got to do now is look at the question again. We've got to, I think that's the end of step 1. That's delta P, isn't it? Yeah? All right. Let's go for step. Oh, what have I said? Oh, okay. It's approximately equal to. I'm just trying to push the point home that we're saying that delta P doesn't equal that. It's approximately equal to that, yeah? That's why there's squiggly wiggly things instead of the equal sign between the two lots of things there is there. Now here's step 2. So therefore I'm going to get delta P over P, okay? So that's what that next line is about, because P, or F of L as they call it, is just K root L. So I'm just putting that on the denominator, and that's what we've got. Now, there's some lovely things are going to cancel now. Yes, goodbye Mr. K, we don't need you. And we don't need the root L's because they've gone as well. So what are we saying? That delta P over P is 5/400. Good heavens above. Now, all we've got left to do now is times that by 100 to get percentage change. The percentage error, or changes, the error as they call it. And what's that come to? Yes, you saw it. Yes, you've got it. Yeah, it's 5/4 or 1.25%. Now, look, we whittled that thing down from a monstrous looking thing to something very simple by just keeping our head, working a strategy out and going for it, okay? Aren't you proud of yourself? You see, you hung in there, and I'm sure you could do that if you just do the thing step by step, noting what the procedure is, the underlying procedure. Yeah, Mr. Box, thank you for coming. Now here's another one. Okay, what's this? Given that y equals 10 minus 5 over x, and that the value of y, increases from 5 by a small amount p over 10, find in terms of p the approximate change in x, and in part b the corresponding percentage change in x. Yeah, look, they're just trying to be smart Alex here, guys. They're changing y, and they're asking us for the change in x. But look, they can't fool us. What we can easily do, I'll show you. Read the question carefully, of course you've got to do that, and then underline the key facts. So let's do that. That's the function. And yes, they're changing the value of y. Y, oh, y. Don't worry. We will fix them. Yes, okay, we've got it, Mr. Computer, don't worry. We're well aware of it. And it's changing from 5, so that's ground 0 for y. Okay, that's y0. And they're changing y by a small amount, p over 10, trying to confuse us with their pronumerals, but they won't succeed. And we look for the approximate. Yeah, that means linear approximation throughout the nation. And then we've got to get the corresponding percentage. Well, that bit's very easy. Once we get the fractional change in x, we just times it by 100. That's what you do. Now, I've just got myself a little brainwave here about how we handle this switch of variables here. It's going to be so easy. We'll fix them. Now, strategy. Here it is revealed, folks. Number 1. Because we are changing y and not x, and we're used to changing x, what we can do is meet them at their own game. And we can just express x as a function of y. Why not? We can do that. We could put x on the vertical axis in a graph and y on the horizontal axis. There's nothing to stop us doing that. So we'll fix them up, won't we? let's do that. And we use the linear approximation technique as delta x this time is approximately equal to h times dx dy. You see, there's no reason why we can't do that at the point y0, ground zero, and where h, or delta y, is p over 10. And that would be part A. They just want the approximate change in x, or delta x. Okay? See, no problem now that we've done the switch in variables there. And part 3, of course, is for part B, we just multiply the whole thing by 100 and we're done. Easy, easy, easy. Okay, let's go for it now. We've got to change this thing around, so we're making x a subject now. So we've got y is, yes, I've just basically common denominated that thing, and now I'm going to do some algebra to work out what x is in terms of y. So multiply both sides by x, gets that. Rearrange the formula so I've got all the x terms on the left hand side, you get that. Divide by the y minus 10 in brackets term, and you get that. Very satisfactory. Now, we've got to get, it's easy now, we're just going to do dx dy. Simple as, and that cleaned up is that. No problem. So now we're just, we've completed step 1, and we're going to do the step 2, I think now. So when y is y0, which is 5, okay, remember, yep, y0 was originally 5, so therefore dx dy at y0 would be subbing in 5 for the y term, okay? And what do we get? 5 over 25, which is basically 1/5. Now that is dx dy at ground zero, or where y is y0, which happens to be 5. I think we're ready to use our formula now, because we've got h, haven't we? H was p over 10, and we've got dx dy at y at ground zero. There it is. It's so easy, it's so easy, so easy. Look at that, just falls off the page like that, you know, like as easy as falling off a log. So I think Mr. Box is coming to help us in a minute. Oh yes, so I'm just saying delta x is approximately equal to p over 50. Thank you, Mr. Box. Now, what else have we got to do with this silly thing? Oh yes, we've got to do part B, don't we? Well, that's easy, easy as. So therefore part B, we actually we haven't got a little piece of the jigsaw. We haven't got x when y is 5, because we've got to do delta x over x at ground zero times 100 to get part B done. Okay, and we haven't got that value of x, so we're just going to do a bit of subbing in for y equals 5, and we'll work out what x is. Into the original equation, that is, okay? So y is 5 equals 10 minus 5 over x, and just do some algebra to work out what x is. Now, can you see what x is? It's sticking out a mile. X is going to be 1, I think, wouldn't you say? Yes, we had to change screens. Therefore, x is 1. Yeah, that's it. All right, we're nearly done. That's x at ground zero. Therefore, remember what we're trying to do. X over x at ground zero times 100 is the percentage change in x, and that's looking pretty good. It looks like 2p to me, for you and me. 2p% change in x. Very satisfying, eh? Now, come on, you could do that. You can do that. You've just got to remember the principles of what you're doing, and don't get lost in all the symbols everywhere. Okay, now what's this last one? Okay, we're differentiating 1 over root x with respect to x, and we're using the result to find an approximate value for 1 over 100.5. Well now, did you see that word approximate? That's your cue. That's your cue. Now, this is a little bit tricky, because you've got to work out, see that 1 over 100 root of 100.5, you've got to work out what, you've got to interpret that to get an h term and an x at ground zero term, see, from that expression. So you've got to use your mental acuity to figure out the best way forward with this. That's the problem with this one. But it's not that hard. Yes, linear approximation, we know that, folks, we know. And let's go. Yes, now I'm saying, that's right, I'm saying x is 100. I mean, you know, it's not rocket science, and therefore delta x is 0.5, a little bit more than 100. Yeah? Very simple. All right, our strategy. Now, the strategy is very simple. You reread the question again. We're looking for an approximate value, not an increment this time. We're looking for an approximate value of 1 over root 100.5. So, this is what we do. We let y equal 1 over root x. We let ground zero for x equal to be 100. We let h equal 0.1. Now, that's the first major step forward. Now, we just follow the procedure now. Therefore, we find dy dx when x0 equals 100. And then we find delta y. We're going to remember we said y equals, they didn't say that, but we're defining y equals 1 over root x. Delta y would be approximately equal to h times dy dx at x0, wouldn't it? Now that's delta y, but we need y1, the new value of y, don't we? So we've got to work that bit out as well now. So therefore, we'll find, first of all, we'll find what y0 is. That's when x0 equals 100. That's just plugging into the formula for y equals 1 over root x. And then, the knockout punch, we'll find y1, the new value of y, which means, in other words, 1 over root of 100.5, would approximately be equal to y0 found in the previous step plus h times dy dx at ground zero. Now, that's easy as, so come on, we'll go and do it together. Right, we let y equal 1 over root x when x is 100 and x0, is 100 and h is 0.1. Step 2, okay, we're saying that y is x to the minus a half, because I'm going to differentiate it now. Dy dx is minus a half x to the minus 3 on 2. Okay, easy as. Now, therefore, what does that come to? Just cleaning it up a bit. Minus 1 over 2 times x to the 3 over 2. And then when x is 100, that's x0, we're subbing in. Now look at that. Dy dx is minus 1 over 2 times. Now, in case you didn't realise, 100 to the 3 on 2. Now the way I've worked that out is 100 to the half is 10, and then 10 cubed is 1,000. Okay? Alright, snail trail. Now that's minus 1 over 2,000. So that is the value of the gradient of that function y equals 1 over root x when x is 100. Okay? Now, that's part of that term goes into our formula, defined there in step 5 of the strategy. Okay? Right, now, what else have we got to do? We know what h is, don't we? Yeah, hence delta y is h times dy dx at x0, and let's just plug it in now. It's a half because, remember, we said that delta x or h was 0.5. Look at that little green bit up there on the top right corner where I worked out what x was and what delta x was. So that I've just plugged that in as a half in that formula. So it looks like delta y is minus 1 over 4,000. Yes? Okay. My goodness. Now, this is excellent. So now we've got to get the actual value of y, the new value or estimated value of y. So here it comes. Oh no, this is the bit where we're working out y0. This is when x0 is 100, y0 will be 1 over root of 100, which will be 1 over 10. Now step 5. Hence we can say, here's the knockout punch. y1 will be approximately equal to y0, which we just found in the line above, 1/10, minus 1/4000th, which we found 1, 2, 3, 4 lines up. Okay? And that's it, folks. That's it. Now we've just got to probably make that a little bit more reasonable, very simplified a bit. I'm going to do an LCM on it of 4,000. Lowest common multiple, that is, guys. That becomes, did you see how I did that? Multiplied the first term by 400 over 400 to make the denominator 4,000. And I got 400 over 4,000 minus 1 over 4,000. And you get 399 over 4,000. So that is the value we are seeking. Okay? My goodness, how sweet it is. Therefore, yeah, that's what I'm saying. 1 over square root of 100.5 is approximately equal to 399 over 4,000, and I've left that as an exact value because they didn't say anything about decimals. So, there we go. That's the... Oh, that bit wasn't supposed to be there. I'll just rub that out just a moment. And there we are. So we're all finished, and I hope you enjoyed that. It's not difficult, so just have a go at it and do your best, okay? See you next time.